All right, there we go. So this is week 5, chapter 4, describing the relation between two variables. So a couple of reminders. Homework number 5 for week 5, chapter 4, due by Sunday at 11:59 p.m. Eastern Standard Time, as well as your chapters 1 to 3, test number 1, same due date, Sunday, 11:59 p.m. Eastern Standard Time. So by the end of this session, you should be able to draw and interpret scatter diagrams, describe the properties of the linear correlation coefficient, or the LCC, estimate the LCC, or the linear correlation coefficient based on a scatter diagram, find the least squares regression line, or the SR line, use the LSR line to make predictions, interpret the slope and y-intercept of the LSR line, and compute the marginal distribution of a variable. All right, so let's begin with section 4.1, which is all about scatter diagrams and correlation. So in this section, you will be able to draw and interpret scatter diagrams, describe the properties of the linear correlation coefficient, estimate the LCC based on a scatter diagram, and compute and interpret the LCC. So in chapter 3, we look at numerically summarizing data from one variable. But oftentimes in newspaper articles and studies frequently describe the relationship between two variables, which is similar to the article that I'm going to let you read. Do SAT scores really predict success? So I'm going to send to you the link through chat for this one, and then I'll give you time to read the article, and then we're going to more about it. So let me see if I can send to you the link through chat. Hopefully that's successful. All right, did you get the link?
Yes.
All right, I'm going to give you time to read about it, and then after that, talk a little bit more about what's going on with that article. All right?
All right.
All right, good. So can you tell me what do you think about the article?
It's interesting how they're trying to do if there's any relevancy for.
For the GPA and SAT score, right? So in that article, it's there's what we call the response variable, which is the GPA, which whose values can be explained at least in part by a predictor variable, which is the SAT score. So they're trying to compare if there's really a relationship between the GPA and SAT score, right?
Yes.
But remember, unless we perform a design experiment, we can only claim an association between the predictor and response variable and not a causation. So when we say design experiment, that means we're going to test a hypothesis, like really displaying if the GPA has something to do with the SAT score as well. So that's only true when we perform that design experiment. But as of right now, because this is just an article, we can just say that this is only a association for these two variables. So our goal in this chapter will be to find ways to describe relationships like the one between the student SAT score and the GPA. And to describe the strength of that relationship, first we need a new type of graph. And let's call it a scatter diagram. So scatter diagrams are the easiest way to graphically represent the relationship between two quantitative variables. They're just XY plots. So with the predictor variable as the X and the response variable as the Y. So let's have this scenario. So below, the data below are the heart rates of students from a statistics 1 class at FCC during the spring semester. So students measured their heart rates in beats per minute and then took a brisk walk and measured their heart rates again. So here's the before and after result. So we can see that the heart rate before going on the walk is the predictor, which is the X. And the heart rate after the walk is the response, which is going to be the Y. This is what it looks like when we plot them. All right. Now here's an excellent video. I'm going to show it to you first before we move on, showing a scatter diagram on countries' development created by the BBC. I'm going to play it.
Visualization is right at the heart of my own work too. I teach global health. And I know having the data is not enough. I have to show it in ways people both enjoy and understand. Now, I'm going to try something I've never done before. Animating the data in real space, with a bit of technical assistance from the crew. So, here we go. First, an axis for health. Life expectancy, from 25 years to 75 years. And down, an axis for wealth, income per person, $400, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubble showed the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40. The UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe! And now I speed up through the 1920s and the 1930s. And in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948. 1948 was a great year. The war was over, Sweden topped the medal table at the Winter Olympics, and I was born. But the differences between the countries of the world was wider than ever. The United States was in the front, Japan was catching up. Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh, and Indonesia, they were still poor and sick down here. But look what is about to happen. Here we go again. In my lifetime, former colonies gained independence, and then finally they started to get healthier and healthier and healthier. And in the 1970s, then countries in Asia and Latin America started to catch up with the Western countries. They became the emerging economies. Some in Africa follows. Some Africans were stuck in civil war and others hit by HIV. And now we can see the world today in the most up-to-date statistics. Most people today live in the middle, but there are huge differences at the same time between the best of countries and the worst of countries. And there are also huge inequalities within countries. These bubbles show country averages, but I can split them. Take China, I can split it into provinces. There goes Shanghai. It has the same wealth and health as Italy today. And there is the poor inland province Guizhou. It is like Pakistan. And if I split it further, the rural parts are like Ghana in Africa. And yet, despite the enormous disparities today, we have seen 200 years of remarkable progress. That huge historical gap between the West and the rest is now closing. We have become an entirely new converging world. And I see a clear trend into the future. With trade, green technology, and peace, it's fully possible that everyone can make it to the healthy, wealthy corner. Well, what you have seen in the last few minutes is a story of 200 countries shown over 200 years and beyond. It involved plotting of 120,000 numbers. Pretty neat, huh?
There you go. Very nice, huh? All right, so not all the relationships have to be linear, just like what we saw in the video and the before and after heart rate data in earlier example. We have types of relationships, or sometimes we don't have any relationship at all. Here are some of the relationships that may be described using the diagram. So this one plays linear relationship between the predictor and the response. This is also linear relationship between the predictor and the response, but different directions. So the relationship is nonlinear in this case between the predictor and the response, and no relation at all for this particular picture. So the next thing we need to do is somehow quantify the strength and direction of the relationship between two variables. Here's how we'll describe the direction. So the next images will show examples of what scatter plots might look like for two positively associated variables. So these are all positive because when we read our dots, the plots from left to right, it's going up. And these are some examples of what scatter plots might look like for two negatively associated variables. So when we read it from left to right, it's decreasing. So in general, we say two linearly related variables are positively associated if an increase in one causes an increase in the other, which is the first linear image. And then we say two linearly related variables are negatively associated if an increase in one causes a decrease in the other, which is the second linear image that we have. All right. As we can see from examples, knowing the directions isn't enough. We need to quantify the strength of the relationship as well. What we'll need to do is what we call the linear correlation coefficient. So this is a new statistic. So we're gonna only in this class we're gonna be dealing solely with linear relationships. All right. So here's the formula to find the linear correlation coefficient. So I know this looks quite mouthful, but I'm pretty sure you already know how to use your calculator to find the these values. Do you have any questions? And were you able to use your calculator when you were using when you were doing your homework?
Yes.
All right, so you're good with this.
Yes.
Using calculator. All right. So some of the properties, a quick summary of some of the properties of linear correlation coefficient. So the linear correlation coefficient is always between -1 and 1. And if r is equal to +1, there is a perfect positive linear relation between the two variables. If r is equal to -1, there is a perfect negative linear correlation between the two variables. The closer r is to +1, the stronger is the evidence of positive association between the two variables. The closer r is to -1, the stronger is the evidence of negative association between two variables. If r is close to 0, there is little or no evidence of a linear relation between the two variables. And this does not mean there is no relation, only that there is no linear relation. All right. So let's try to calculate a correlation ourselves. To make our data set a bit more manageable, let's use the before-after data from example 1 in section 4.1. So the heart rates of students before and after a brisk walk. But let's just use first 8 of our sample. Let's find the linear correlation coefficient. So if you have your calculator, you can try to find the linear coefficient for this data, if you want to try.
.987.
That's right. So we got 0.987, or we can round it up to 0.99. So just showing how to calculate that. So since we have the sum 6.90032 for this column, the last column on the right. And since we have um, eight numbers of data, so we're gonna from the formula n minus 1, so we're gonna divide this sum, the 6.90032 by 7, and we're gonna have 0.99. So the 0.99 is very close to 1. So, and also when we look at our graph, so it is very, we can see that it's very strong. It's fairly high. There, the relationship is very high. We look at our graph. All right. So let's try this one more time. So research performed at NASA and led by Emily R. Maury Holton measured the length of the right humerus and right tibia in 11 rats that were sent to space on Space Lab Life Sciences 2. The following data were collected. Let us, I don't know if you have a piece of paper there to draw the scatter plot, or you can use your calculator to see what does it look like. So draw a scatter plot diagram treating the length of the right humerus as the explanatory variable. So that's going to be our y, and the length of the right tibia as the response variable, which is the x. And then compute the linear correlation coefficient between the length of the right humerus and the length of the right tibia. And does the linear relation exist between the length of the right humerus and the length of the right tibia? I'll give you time to do that. You said 0.95?
Yes.
Nice. How about, does a linear relation exist between the length of the right humerus and the length of the right tibia? So based on your linear correlation, do they have relation?
It seems like they are.
Yes, that's right. They have, because it's 0.9 and it's close to 1, and it's a positive association. That's right.
Okay.
Mhm. Right. So if you do you know how to um, use the graph or see the graph in your calculator?
If you could just refresh me.
Okay, so I don't know. Let me see if I can share to you my calculator app. Give me one sec. I have to figure this out. All right, let me share application. All right, I think I'm gonna have to stop sharing this first and then sharing you one. All right, and then sharing you one. All right, let me see. There you go. Do you see my calculator?
Yes.
Okay, let me see. This is not the data, I think. Let me make it smaller. And go to stat. I'm gonna make sure you have um, your data in your L1 or L2 in your calculator. I deleted my L1 and L2 and L3 as well. That's why I have L4 and L5 here. So if this is your data, you know how to get here, right? So you go to stat, go to edit, just choose one. And then if you want to see the plot, the graph, so you just go to second and then the start plot, the y equals, and then make sure you choose one and make sure it's on. Click on, and then you can go also to type the scatter plot, highlight that, and then highlight L1 or whichever whatever table you populated. So in my case, it's L4 and L5. I'm gonna change that to L4. Just a second, and then L5, and then you can just hit the graph. So the window might look off because this is just the Y half of like the first quadrant showing. Um, you can go to window and adjust this so that you can see the whole graph. You got it?
Yes.
All right. So that's how you graph the scatter plot. All right. Let me see again. Let's see if I can continue. Okay, so this is what the graph should look like, our scatter plot. So mine is not like the window is not correctly set up, so I didn't show the dots. But you can always adjust the window. All right.
Got it.
All right. I think we have another example. So this time, the following data are based on a study for drilling rock. The researchers wanted to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So depth at which drilling begins is the explanatory variable x, and the time in minutes to drill 5 feet is the response variable. So here's the data. So let's find, uh, of course, we're going to draw later. I'm going to show you again, draw the scatter plot, and then determine the linear correlation coefficient. And does a linear relation exist between depth and drilling time, and why? I'm going to give you time to do that.
Yeah. 0.77.
That's right. So the question number 3, does a linear relation exist between depth and drilling time, and why? So we're going to use this table, the table that we call the critical values for correlation coefficient. So you said you have 0.77,
Yes.
0.773. So since we have, how many data we have? 2, 3, 4, 5, 6,
12.
12. So when we look at the table, we have 12, the n is equal to 12, and the critical value is 0.576. So we can answer question number 3 by using that table. We can say that there is a relation because 0.773 is greater than the critical value when your data, which is 0.576 only. So is your linear correlation value, which is 0.77, is greater than the 0.576. So we can say that there is a correlation. So this table, I'm gonna upload this also in our Blackboard under course materials, just in case we need it. But in your homework, I don't think this is required. Right?
No, it wasn't.
Yeah. So just in case.
Got it.
All right. And then the graph, if we use our calculator and see the scatter plots, this is what it should look like. So 0.77 is not really close to 1, so that's why it's kind of scattered. All right. Do you want another one? I have another one.
Sure.
All right. So here's, I think this is the last one. So age versus the HDL cholesterol. So a doctor wanted to determine whether a relation exists between a male's age and his HDL, so-called good cholesterol. He randomly selected 17 of his patients and determined their HDL cholesterol levels. He obtained the following data. There you go. So same questions. Now draw a scatter diagram, compute the linear correlation coefficient, and there's a linear relation exists between age and DHL cholesterol.
So negative 0.16.
That's right. It's negative. Good. Okay. So now the question, does a linear relation exist between age and DHL cholesterol? So let me go back to the table, but you can count how many respondents, the data we have.
17.
17. All right, let's go back to the table so that we can answer that.
So 0.482.
All right. So you said your answer was negative 0.16. So can we answer the question? Does a linear relation exist between age and DHL cholesterol?
I would say no, it does not.
Because that's correct, because it is
That what the critical value is not met.
that's right. Is your actual answer, the linear correlation is less than the critical value. So there's no
Okay.
correlation. Mhm. All right. And here's the scatter diagram. So it's all over the place. That's why it makes sense in our uh, answering question number 3.
Got it.
All right. That's section 4.1. All right. Now let's go to section 4.2, the least squares regression. All right. You ready or you want to take a break?
I'm ready.
All right. So by the end of this section, you will be able to find the least squares regression or the LSR line, use the LSR line to make predictions, and interpret the slope and y-intercept of the LSR line. So before we move on further with this LSR line, it's important for us to remember a familiar concept in algebra. All right, if there's one thing we all remember about lines, it's the slope-intercept form of a line, which is the famous y equals mx plus b, where m is the slope of the line and b is the y-intercept. Knowing the form isn't enough, we also need to know what each part means. So let's start with the slope. So most of us remember the slope as rise over run, but that only helps us graph lines. What we really need to know is what the slope represents in terms of the original two variables. Let's look at an example to see what we can get, if we can get the idea. So example, the equation t equals 6x plus 53. So roughly approximates the tuition per credit at FCC since 2001. I just made it up. The graph below illustrate the relationship. All right. So in this case, X represents the number of years since 2001, and T represents the tuition amount for that year. In this example, we can see that both the 6 and the 53 have very specific meanings. The 6 is the increase per year, and um, the 53 is going to represent the initial tuition for the tuition per credit hour in 2001. So as we progress into the relationship between two variables, it's important to keep in mind these meanings behind the slope and the y-intercept. Right? So another very important skill also is finding the equation for a line. In particular, it's important for us to know how to find the equation when we are given 2 points. A very useful equation to know is the point-slope form for, for a line. Let's practice using this form to find an equation for the line. So the equation, the point-slope form is a y minus y sub 1 equals m times the quantity of x minus x sub 1. Example 1 from section 4.1, we talk about the relationship between student heart rates in beats per minute before and after a brisk walk. Let's highlight a pair of points on that plot and use those points to find an equation for a line that might fit the scatter diagram. All right, so let's use 52, 56 and 90, 116. So using these 2 points, first let's find the slope, which is going to be approximately 1.58. So remember the equation for the slope is y sub 1 minus y sub 2 divided by x sub 1, I mean x sub 2 minus x sub 1. So plugging in the given 2 points, we will end up having approximately 1.58. So that's going to be our result. So the equation for the line would be y equals 1 minus 26.16 after we do the math using the points form. Excuse me. All right. So also, it's interesting to note the meanings behind the slope and y-intercept. For this example, a slope of 1.58 means 2 additional beats per minute before the brisk walk. The heart rate after the walk was 1.59 back. The y-intercept, on the other hand, doesn't apply in this case. A y-intercept of negative 26.16 means that if you have 0 beats per minute before the walk, you'll have negative 26.16 beats per minute after the walk, which doesn't make sense. So that brings up a very important point that models have limitations also. In this case, we say that the y-intercept is outside the scope of the model. Okay. All right, so now that we know how to find an equation that fits the data, we need a strategy to find the best line. Right. So let's work our way up to it. So unless the data line up perfectly. So if the data doesn't line up perfectly, we will have a residual. So residual is the difference between the observed and predicted values for y. So notice here that we use the symbol y hat. This is the standard notation for statistics. Using the hat symbol over a variable notes that it is predicted. Let's again use the data from example 1 from section 4.1. In example 2 earlier, we found the model y equals 1.58x minus 26.16. So let's use this model to predict the after heart rate for a particular student, the one whose before heart rate was 86 beats per minute. So the predicted heart rate y equals 1.58 times 86 minus 26.16 will have 109.72 beats. So using that predicted heart rate, residual will be equal to negative 11.72. So here the residual is negative since the predicted value was more than the actual observed after heart rate. So here's the on a particular student. So this is the scatter diagram earlier. The residual when we pick the student with the 86 beats per minute, the residual will be negative 11.72. So here's the zoom in picture. So it's below that line. That's why it's residual. There's an error.
Got it.
All right. So how do we determine which line is the best? The most popular technique is to make the sum of the squares of the residuals as small as possible. So kind of like the same with variance on the previous chapter. So we're gonna square it. So the method is called the least squares. Um, the method of least squares. All right. So here's the formula for the least squares. We're not gonna do this. We're gonna use the calculator to find the equation of the line that best fit. Right. So here's an example. So let's again use the data from example 1 in section 4.1, but instead of just using 2 points to get a line, we'll use the method of least squares to find the least squares regression line. So here's the data. Do you know how to get the residual and then the equation from your calculator?
Me real quick and like
All right, let me show you. Let me stop sharing this and then I'll sharing you one. Give me one sec. Okay, so here. So for you, I think this is also in your, what you call it, the homework, like the line, to find the line. Let me see. So the data, I don't know if you can see the data in your screen, or you just
No,
see
I'm just seeing your calculate tab.
just the calculator. So I'm gonna put in
Yeah.
the calculator, I mean the the data in my calculator. So I'm gonna put, so this is not it. So I'm gonna clear it first. All right. So I got 86, 62, 52, 90, 66, 80, 78. I apologize, it'll take time. 58, 64, 72, 68, 60, 80, 66, and 76. All right, next is 98, and then 76, 96, 86, 84, 128, 74, 106, 84, 96, 82, 78, 90. All right, almost there. 92, 70, 92, 116, 114, 116, and 94. All right. So for us to find the R in the equation, so remember our equation is y equals mx plus b. So the R first, so you're gonna go to let me see if I can remember this. Stat, calculate. You can go to linear reg, the ax plus b,
Okay.
and then make sure the x list and y list you have the where you put your data, and then calculate. So this is your y equals mx plus b. So the y equals ax plus b there. Your a is going to be, I don't know what that a is. That's your just your slope. That's 0.8473. And then your b, your y-intercept is 29.6. The residual is going to be 0.4864. So again, you're going to go to stat, calculate, and choose number 4 for linear regression, ax plus b, and then enter
Okay.
again. All right, there you go. That's how you got your R. You good? All right, let's try
Yes.
it. Let me share the screen again. All right, let's try this one. So this is the data earlier with the NASA. So let's find the least squares regression. The line, the in the form y equals mx plus b. Treating the length of the right humerus as x, explanatory variable, and the length of the right tibia as y. And then interpret the slope and appropriate, and also determine the residual of the length of the right humerus if the length of the right humerus is 26.11 and the actual length of the right tibia is 37.96 millimeter. Is the length of this tibia above or below average? Okay, if you have y hat equals 1.3902x plus 1.140, then your line equation of the line is correct. For number 2, interpret the slope and y-intercept if appropriate. So in this case, if the humerus increases in length by 1 millimeter, the length of the tibia increases by about 1.3902 millimeter on the average. And then the residual is equal to 0.458 millimeter, and it is above average. All right, let's continue. Here's another example. So the same, find the least squares regression line, treating depth x as the explanatory variable and the time to drill y as the response variable. And then interpret the slope and intercept if appropriate, and then use the regression line to predict the time to drill 5 feet of drilling begins at 100 feet. If your y hat or your equation of the regression line is 0.0116x plus 5.5273, then your answer is correct. the slope here is the 0.0116x, and the y-intercept is 5.5273. So interpreting the slope, if depth at which drilling begins increases 1 foot, the time to drill 5 feet increases by 0.0116 minutes on average. And then the y-intercept, the time to drill an additional 5 feet when starting from the surface is when x is equal to 0 is 5.5273. And the residual is going to be 6.69 minutes. Hey Nick, you're back. I just
I'm back
continued.
again, yeah.
Huh?
So I'm back again.
Yeah, I just continued because for the purpose of recording. Yeah.
That's fine, I understand.
All right. So that's the second example to find the least square regression line. All right. Do you know how to find it? I think I showed you already to find the equation, right?
Back again.
All right. Do you want to try this? Because this is the last example. It's up to you.
This is when we're finding the equation of the line.
Yeah, the equation of the line, the y hat.
So I got y equals 0.011 for the slope, and then the y 5.527.
That's right. Mm-hmm.
Okay.
And
I'm
then,
getting it for the bits and pieces my connection is not helping me with.
all right, I understand. But do you have any question? Because this is the last one. This is the last
No, I
question.
don't have any questions. Two questions not pertaining to.
Can you say it again?
Two questions not about tonight's lesson, just about so.
Oh yeah, sure, sure. Let me just
You want to?
let me just stop the recording. Hold on.
Okay.